Okay, this is the Introduction to Hypothesis Testing chapter, otherwise known as hypotesting, just for to say quicker. First, what's the logic of hypotesting? Basically, that we have no or limited access to the population. So we don't have access to the population, so we have to rely on samples. So it allows us as researchers to use data from samples to make inferences about the population, which is more often the case than not because it's difficult to get population data. So what is a hypothesis test? It's a statistical method that uses sample data to evaluate a hypothesis about a population. So that's the official textbook answer on what is a hypotest. So basically, hypotests are used in the context of research studies. You really won't see it beyond the context of research studies. Occasionally they might mention them on the news, but it's really in the genre of published research. So the goal is to determine whether a treatment, intervention, whatever you want to call it, has any effect on individuals in a population. So in this sense, we make inferences, and this is when we get into what we call inferential statistics. So an example is performance on the Wisconsin card sorting test. And the general idea behind it is that ability declines with age, that people are less able to sort the cards with the same agility, speed, accuracy with age. So we have a sample of individuals, or actually, this is the population. For individuals age 65 and over, meaning it's been normed, there is a mu indicating a population mean equals 80, and a standard deviation, the lowercase sigma, indicating a standard deviation of 20. So these are the population parameters. And then we sample 25 adults age 65 and older, giving each participant a blueberry supplement. So let's say we want to look at the effect of blueberries on performance on the Wisconsin card sorting test. So we're basically wanting to determine whether the ability increases or decreases as a result of a blueberry supplement, so the actual performance on the test. So our H sub O, and when I say sub, it means subscript. So H subscript 0 or O, H sub O, or null hypothesis is mu with supplement equals 80. And remember the parameter here was 80. So population parameter mean was 80. So we're saying that it doesn't matter whether or not you give them blueberries, their performance on the test is not going to increase. So that's going to be the exact same as it was before. It's going to be equal to the population parameter. So otherwise stating it, blueberry supplements will have no effect on Wisconsin card sorting test performance, which has a mu of 80. So that's another way of saying it. So our null, or H sub O, states that in general, the population, there is no change or difference. So we state that the blueberries have no effect, but the alternative, or H sub 1, or H sub A, or H, which is alternative, and the 1 refers to, you can have several alternative hypotheses. You can have H sub 1, H sub 2, H sub 3, but in this case, it's just going to be 1. States that in the general population, there is a change or difference. So we, as researchers, we want to find some sort of effect, but we know that more often than not, there is a null meaning 0 effect of a certain treatment that we've reviewed the literature and we hope that there's a difference, but we don't actually know yet until we actually get a sample of individuals, have them take the blueberry supplement, and then subsequently test them. So the H sub 1, or the alternative hypothesis, would be H sub 1 mu with supplement does not equal 80. That there's some kind of effect on the performance, thus the mu is not 80. Now this is a non-directional test because it's just stating it's not 80. Now, can you state a directionality? Yes, definitely. But you usually have to go by your literature. Your literature will say, okay, there's evidence to suggest that the blueberry supplement will be associated with improved performance on the Wisconsin card sorting test. But without the evidence from the literature, it's hard to make that argument that it is a directional test, other than just, well, that's my gut instinct, which that does not suffice. So we next need to set our decision-making criterion. Let me get my arrows going. So if you look at the green arrow and box, it says if M, which is the sample mean, which we're about to get, is close to the mu in the null, which in the null is mu sub 80, then we do not reject the null. So if it's in that range near if our sample mean is near the mu mean, the mu population mean, then we're not going to reject the null. We're going to say, yep, there really is no effect of blueberries. Sorry. Or if our sample mean is not close to the mu, then we reject the null. So if it's in the extreme low or low probability values, then we have evidence to reject the null. Now notice for the non-directional test, we have tails on both ends. So we're just saying it's not 80, and it's either, or the alternative is that it's not 80, so on either end. So it's two-tailed. So when people say it's a two-tailed test, they're referring to a non-directional test because we're looking at both extreme tails of the distribution. We call this criterion for rejecting the null our alpha level or level of significance. So from the textbook, the alpha level or level of significance is a probability that is used to define the very unlikely sample outcomes if the null hypothesis is true. So basically, you set what your alpha level is going to be. So it's typically set at 0.05 or 0.01. Those are just kind of heuristics. For a non-directional test, this 0.05 is half. So you have 0.025 on the lower end and 0.025 on the upper end. And we set our boundaries by our alpha, which is our critical region, which defines our critical region. The critical region is composed of extreme sample values that are very unlikely to be obtained if the null hypothesis is true. The boundaries for the critical region are determined by the alpha level. If sample data fall in the critical region, the null hypothesis is rejected. So, if our sample mean lies in the extreme 5% of scores, meaning 0.025 on the lower end, 0.025 on the upper end, then we reject the null that mu equals 80. So basically we're evaluating alpha equals 0.05 in this case, looking at the extreme 5%, and at the bottom of the figure you'll see right here a critical region extreme 5%. And look, there's the middle 95% with high probability values if A sub O is true. So if you have a sample mean that's within this range of the middle 95%, you don't reject the null. Even if it's like right here, right before, you don't reject the null. But if it passes that alpha mark and is in the critical region, then you can reject. Okay. Wait, but how did you? So how do you know that an alpha of 0.05 corresponds to a z-value of plus or minus 1.96? You refer to a z-score table. No fancy math there. Just you refer to a z-score table. And you look at column C of the table and find the probability of 0.025. And why 0.025? Because in a non-directional test, you take the alpha level that you've decided, which in this case, or most commonly, almost majority is 0.05, and divide it by 2. Now, occasionally you'll have alpha 0.01, but actually that's not too common. So it's more likely 0.05. And that's more of a heuristic in the field because people ask me, why not alpha 0.10? This is kind of what the field has come to accept. So this corresponds to a value or a z-score value of 1 plus or minus 1.96. Okay. Then we calculate our test statistic. So we calculate our test statistic, and when I say test statistic, I'm referring to from your sample data. So your test statistic is what you calculate from your sample data. So it's mean, sample mean, minus mu, which is whatever you hypothesized. In this case, we hypothesized mu equals 80. So 80 over standard deviation, or actually standard error between the mean and the mu. In other words, stated otherwise, sample mean minus hypothesized population mean for what we have chosen to test, our test statistic, and then over divided by the standard error between the mean and the mu. So for our sample of n equals 25, we achieved a mean of 92 with blueberry supplements. Looking good. 92 looks like it's above 80. Then we can begin to plug into values for this formula. So sample mean 92 minus 80, that's 12. Well, what's the standard error? Wait, what is that? So if we have a sample of 25, we must calculate standard error from the mean. And we get that by dividing the standard deviation over the square root of n. And remember back in the other slide, we were given the mean and standard deviation. Let me go see if I can go back to it real quick. I might be wasting time here. Yeah, there we go. So he says a mu of 80 and a standard deviation of 20. Okay, so now I need to click all through that. So we know that information. I know I'm going to skip past it. Did I pass? No. Okay, yeah. So we know the standard deviation right here, divided by the square root of n. And the n is 25. Square root of 25 is 5. So 20 over 5 equals 4. That's our standard error. This is the important formula that's going to keep rearing its head. So you might want to commit to memory. Well, I commit to memory, but you know. So standard error is standard deviation divided by square root of n. I use it often. Then we calculate our test statistic, which is mean minus mu over standard error. So 92 over minus 80 is 12. 12 divided by 4 is 3. Looking pretty good. And a z-score of 3 is way out. Yeah, I see our blueberry eaters are way out here. So, yeah, do you reject the null? Yeah, you do. Because remember our z value was plus or minus 1.96, and 3 is definitely greater than 1.96. So, type 1 error. Type 1 error occurs when the researcher rejects the null when it's true. So you have a null hypothesis that's true, that, hey, there is no effect. We say there is, let's say there was no effect of blueberries, okay? So there was no effect of blueberries, but we reject the null anyway, when really there is none. And so is that such a bad thing? It depends on the consequences of the research, but generally type 1 error is considered worse than type 2 error. So what I mean by that is, okay, well, in the context of blueberries, let's say you say there's some great effect of blueberries when there isn't a. What's the harm of that? People eat more blueberries? You know, like context kind of dictates, well, what is the harm of that? And now if you give people blueberries or over giving them an actual treatment that could actually help them, I could see the harm there. So instead of giving them some other medication or treatment or supplement. Say, oh, no, just give them blueberries when there's really something else there out there that could help them. I can see the harm there. But blueberries alone, like, oh, well, you get some extra vitamin C or whatever. So a lot of it depends on context. But it's generally considered worse. The alpha level or level of significance, e.g. 0.05, is the probability or likelihood that a test will lead to a type 1 error. So the likelihood, so saying you have an alpha of 0.05, that's saying that's the likelihood of you're having a type 1, of committing a type 1 error. And generally, we consider that to be acceptable, that there's a 5% chance of rejecting the null when it is true. And that's more heuristic than anything. Like, there's not, the field as a whole kind of decided 0.05 or below is what we're willing to accept in terms of type 1 error. Type 2 error occurs when the researcher fails to reject a null hypothesis when it is really false. So you fail to reject the null that blueberries actually do help, but you fail to find that, and you fail to reject it. Okay, so people don't get to have this wonderful blueberry supplement treatment that would really help them, so they fail to do that. So another example would be Acebo, you're innocent. So you're innocent. That's the null hypothesis in our criminal justice system in the U.S., that you are innocent until proven guilty. But the jury finds you not guilty. They say, oh, yeah, you're not guilty. But uh-oh, you actually did. You actually did murder your boyfriend or whatever, spouse. And so you actually did murder this person or whatever. And you turn out, so you're actually guilty, but they don't actually reject the null. They fail to reject the null hypothesis. And so, yeah. And that's just another argument of why type 1 error is considered worse, because what if they reject the null that you are innocent, and it turns out you really didn't do it? The null hypothesis is true, So type 1 error would be rejecting the null hypothesis that, you are innocent when it's actually true. And you get sent to jail, and you spend the rest of your life in jail, and it's horrible, and yeah. So anyway. So, I probably should back up a little bit. Type 1 versus type 2 error. This is a little table. So as a researcher or experimenter, you have two decisions. You can reject the H sub O, the null, or you can retain it. Now, when the H sub O is true and you reject it, that's a type 1 error. So it's when it's true, like, hey, there really is no effect, but you're saying there is. You're rejecting it, saying, oh, reject the H sub O. That's a type 1 error. When the effect exists, so let's say blueberries really do help and the H sub O is false and you reject the H sub O, that's a good decision. Good decision right there. Another good decision is when you retain the H sub O and there is no effect. You say, yep, the null's right, and there is no effect. So that's a good decision here. Then you have the type 2 error. Again, so you do not reject the null, but it's actually false. So that's alpha and beta. So alpha is a level of significance. So you see alpha 0.05 or alpha 0.01, and that's your level of type 1 error that you're willing to tolerate. I'm willing to tolerate a 5% likelihood of committing a type 1 error. And there's beta. Beta is your type 2 error rate. The likelihood or the probability that you're willing to tolerate of retaining an H sub O when it's actually false. The beta rate is usually set at 0.20. That's kind of standard, but you can see some variability there. So, in hypotesting, you have one of two decisions. You could reject the null and conclude that the treatment has an effect, or do not reject the null and conclude that the treatment does not have an effect. So those are your two decisions. Reject the null say the treatment has an effect, or do not reject it. Do not reject and will conclude the treatment does not have an effect. Let me get this all up. Okay, so another example was steps. Let's see if we wanted to examine the effect of prenatal alcohol in rats. Our IV or independent variables alcohol exposure, and our dependent variable is birth weight, and lower birth weight being not so great. Step 1, state the hypotheses and select your alpha level. So our hypotheses are H sub O, mu equals 18 grams. So that would be like the average birth weight of a baby rat, 18 grams. And so for the mu is 18 grams. And then H sub 1, or alternative, would be mu does not equal 18 grams. And we set the critical region. In this case, it'll be alpha 0.05 because that's pretty predominant. So any score above or below C equals plus or minus 1.96. And it's 0.025 in each tail again because we're not imposing a directionality. And so using the information, the following information, we can go 15 was our sample mean minus mu, which was 18, over 1 gives us negative 3 over 1, which is z negative 3. So we make a decision. Z of negative 3 is definitely well beyond negative 1.96, so it's definitely in that critical region. That's, wrong number there. We reject the null hypothesis that mu equals 18, not 80. That's from the previous example. So we could say alcohol had a significant effect on the birth weight of newborn rats. Z negative 3, comma, P less than 0.05. So what are the factors that influence hypotest outcomes? Well, the size and the mean difference, obviously, because that's the numerator in your equation. So Z m minus mu over standard error, that's the numerator. The variability of scores, the denominator, which is the standard error, because those go into the equation, and the number of scores in the sample. Obviously, because that's how standard error is calculated as a function of standard deviation over square root of n. What are some assumptions? Some assumptions are random sampling, which is highly desirable in an experimental situation. But if you're having a correlational design, that may not be possible. But you would hope so that your sample is considered generally representative of the population. Independent observations, meaning in this case, like in the Wisconsin car sorting test example, that 2 of the elderly people or people over 65 who were completing the task weren't spouses or relatives, because those observations are not entirely independent. Next, the value of the standard deviation isn't changed by treatment. So this is otherwise known as homogeneity of variances. This assumption is going to follow you throughout your statistics education, so become comfortable with it. Homogeneity of variances. And then normality, that the distribution of data points is normally distributed. We have non-directional and then obviously directional hypotests. It's pretty much the same, except we specify an increase or decrease. So we same steps. We state the hypothesis and select our alpha. So in the Wisconsin card sorting task example, H sub O, mu is less than or equal to 880, and the alternative H sub 1 is mu is greater than 80. We locate our critical region. And using a one-tailed or directional test, the z is 1.65, because now you don't have to have your 0.05. You don't have to divide it by 2. It's because you're specifying a tail. So the extreme 5% is in the right-hand tail. We obtain the sample data and compute the test statistic. So in this case, it'd be 87 minus 80. So 87 is the sample mean, meaning that your sample of individuals who took the task scored at 87 divided by minus 80 over 4, which gives you a resulting z value of 1.75. And we make our decision based upon that. And a z-score of 1.75 is greater than 1.65, which is our critical value. Z-score of 1.75 is definitely in the critical region because it exceeds the value of 1.65. And then we can also calculate an effect size, which is actually pretty important, because you can have a result that's significant but barely significant. It's right in that critical region. And so instead of, like, if your z critical value is 1.65, then the z test statistic value that you calculate is 1.67. So it's barely in that critical region. So your co-z will tell you a matter of meaningful effect size. How meaningful is this number? And Cohen's z is very common. It's the mean difference over the standard deviation. So you take basically m minus mu over standard deviation, not standard error. That's the big difference. You get resulting values, and the magnitude of d will tell you how large of an effect it truly is. So if it's a d of 0.2, it's considered a small effect. And it's also, you can state it as a mean difference around 0.2 standard deviations. Then d of 0.5 is medium, and then d of 0.8 and larger is a large effect. So remember that we're talking about standard deviation, not standard error in the denominator for the Cohen's d formula. And remember that standard error is standard deviation divided by square root of n. You see how that formula haunts you? Okay. Statistical power. Power refers to the probability that the test will correctly reject a false null. So you want your test to have lots of power. You want to be able to reject those ugly false nulls. Power is referred to as 1 minus beta, beta referring to type 2 error rate, or the probability that the researcher will fail to reject a null hypothesis. So going back to this, you have your alpha being type 1 error, your beta being type 2 error, and then you have this box here is 1 minus beta is your probability that you reject a null that is false. So you're making a correct decision, but what is your ability to do that? How much power do you have to do that? And then you also have your 1 minus alpha, which is your sensitivity. But we actually won't cover that in this class. We'll barely touch on power, actually. So that's actually for more advanced stats. So what are the factors that influence power? Larger the sample, larger the power. More sample size, more power. You have more evidence to make that decision and be able to correctly reject a null. Correctly reject a null that is false. Alpha level, lower the alpha level, lower the power, because you're making that critical region smaller and smaller. Your alpha level at 0.05, you have a bigger critical region than if your alpha is 0.01, because you're going further out on the tails of the distribution. At 0.01, the tail is pretty small. The region that you can reject is pretty small. One-tailed versus two-tailed. One-tailed increases power because you're imposing a directionality, and the critical region is obviously going to be larger. Okay, well that's the presentation for hypotesting. Please contact me with any questions.